this sounded like it was not on. Okay, thanks for the introduction. Thanks for coming to my talk. This talk could also be called, what is the minimal theoretical model you need to talk about high temperature superconductivity? This is an ongoing effort I want to report about. Well, high temperature superconductors have been around for more than 30 years now, and the typical structure is relatively complicated. The generic phase diagram I just showed, a typical one, is also very complicated, and the question is, how can we capture that as theoreticians without going in all the details? A complete description would anyways be unfeasible, and probably you wouldn't even learn too much if you knew what each and every electron is doing. So the idea is to come up with models that capture the essential concepts and the mechanism, and the idea is a theory should be as simple as possible, but not simpler. So a typical several step procedure that has been taken in the past is you go into the crystal structure, then you realize that what you have to think about are three orbitals of oxygen and copper, and then it seems that you can simplify that even further, that is already debated, into a single band model which looks like this. Electron sites sitting on a square lattice, and these electrons can hop and they have Coulomb interaction. And the simplest model that people have been discussing for decades now, which all of you, I guess, have seen, is the single-band Hubbard model on a square lattice. You dope it with holes, there's a nearest neighbor hopping, and the Coulomb interaction is just modeled by the on-site repulsion. Okay, so the question is this too simple to explain the richness of the phase diagram? And there are so many features in the phase diagram, and many of them are actually explained quite well. So in this talk, I just concentrate on one aspect, namely we look at zero temperature physics, and we look at two questions: the presence of so-called stripes. I will explain that a bit more for those of you who are not sort of like into that field, and whether power law, D-wave, superconducting correlations are present, which you would then call superconducting order. These are the questions I will ask, and it will be done in two steps. Namely, I will first look at the Hubbard model as you have seen it, just nearest neighbor hopping, and then we will introduce an additional next nearest neighbor hopping for two reasons. First of them, this hopping is present in the real solid and important, and the second reason is that if you want to simulate that model with ultra-cold atoms, which people want to do, there is, beyond the fact that you have to achieve very low temperatures, also the issue that at the moment modeling such a next nearest neighbor hopping is still a little bit elusive. There's now quite a lot of ideas around, it seems, but at the moment people don't really know how to do this. So it makes a difference whether this T prime matters or not. Okay, so let me do, and the experts in the audience, please look away for a second. Let me give an ultra-naive picture of why stuff like stripes and superconductivity might exist in the Hubbard model. If you have a half-filled Hubbard model, which is the slang for 1 electron per site, then the Hubbard model with repulsive interactions has a tendency to become antiferromagnetic. So you get this spin-up, spin-down pattern. But it is hole doped, which means there's a little bit less electrons around than what is needed for that half filling. And so what can happen is that an electron, say this one, can hop. By this delocalization, it will lower its kinetic energy, but on the other hand, it will disrupt the antiferromagnetic order, which is costly in energy. So the system would like to lower its energy, but it's not the best idea possibly. So the idea is, what ways are there out of that? One way out of that is that you say, well, and you should not think about it too literally in real space, but just for the explanation here, we pair holes, say like here, two holes next to each other, because there's quite a lot of them around. And what they now do is they do correlated hopping. So as you can see, there was this kind of the one pair of electrons hopped, or you could say alternatively that the holes hopped. And so now the antiferromagnetic pattern has not been disrupted. This pair of holes is a boson. These are two fermions. And in a second step, these pairs of holes, they could condense to a superconducting system. So this is the one idea why superconductivity is an answer of the system to this hopping versus antiferromagnetic order problem. On the other hand, you could also do something different, and this is now totally exaggerated in the picture. You could form stripes. In the cartoon, the stripe is that I basically take out all the electrons here, so I concentrate the holes locally. In reality, there's just a very high hole density, but it's far from empty. And at the same time, there's a very low magnetic moment here. Obviously, it would be zero. In reality, it would just be relatively low, which means there's lots of holes, lots of motion possible, but because the magnetic moment is low, the cost in magnetic energy is also very low. There's not much interaction partners around. Okay, we will see that in more detail what it looks like. But a question which of course immediately comes up, there are these two mechanisms. Will they cooperate or will they be in competition? That's a theme we will keep in mind. Okay, so this is an old field and has been a hotly debated field of condensed matter physics. So the question what you have, whether it's, for example, this superconductor, it's actually kind of a D-wave superconductor, or whether you have this stripy stuff, this is going back decades. And if I write here a lot more papers, this is kind of totally, I should say, under-exaggeration, because it's probably thousands. Yeah, I mean, I don't know who knows all these papers. There are certainly thousands of papers who have been dealing with this topic, and hundreds of proposals have been made, I would say. I cannot obviously go into that here. But that's not the point, but the point is that this is a field where numerics has always been very important, because analytical techniques are sort of a little bit uncontrolled, and you would like to control them. On the other hand, the problem is the numerical methods for this problem in 2 dimensions are also incredibly challenged. Without going into the details now, perhaps in a minute or so in further slides, it has to be clearly stated that each numerical method, including your pet method, has its own shortcomings. And so it was an idea which was mainly kind of advertised by the Simons collaboration on the many electron problem, that we should get away from everyone does his own little method, but to try to put these methods together and really only believe results where the methods mutually support each other. So they all have problems, but these are different problems. So if they happen to agree on something, the likelihood that the result is correct is pretty high. So I want to first briefly outline results of a work which I have not participated in, which was published in 2017 by these gentlemen here who combined 4 different methods. I will come back later to DMRG, well, quite obviously in my case, and the auxiliary field quantum Monte Carlo, but they looked at the single band Hubbard model for these parameters, which are the ones which sort of like the community has agreed upon that those are the ones you have to look at if you are interested in this topic. And what I want to say, the general theme is the likelihood that the results that these people and people like me have found have been somewhere, somehow in the literature is relatively high with these thousands of papers, but we definitely would decline to accept then that people say, yeah, I told you so right from the beginning. I mean, most of the stuff was totally uncontrolled, and this is what we as a community now want to get away from. So what did these people find? Very briefly, they found that a stripy phase is the ground state. You see here there are holes more concentrated around here. This continues vertically, and so there's a kind of a wavy pattern in terms of the hole density. And at the same time, if you look at the spin moments, they are relatively small where the holes sit, and relatively big where there are few holes. This is the typical picture, except for these stripes, which actually have already been observed a long time ago in experiments on high temperature superconductors. What these people also found is, however, that if you then ask what's the wavelength of this stripy structure is, and this had also been a lot of debate, what's the lambda? The lambda in the experiment was 4, and what they found is, well, in this model, the lambda they get is the lowest energy was for lambda equals 8. But if you are sort of like a bit more honest, you probably would have to say the energies of the stripes for wavelengths between 5 and 8 are almost degenerate. I mean, you see the error bars of the different methods, so they more or less agree, so we can believe that, but still. And also, what they also found, if you have a pure D-wave superconductor, which is not coexisting with stripes, which however are observed, that would be quite a bit higher in energy, but they did not look at the question of stripes coexisting with superconductors. This was already difficult enough. Okay, so after having advertised their work, so this is when sort of like we, and this is the group of those people within this collaboration, now a subset of people doing QMC under the leadership of Shivei Zhang, and here the DMRG crowd, a postdoc and PhD student of mine, and actually Jiamin was also a postdoc of Steve. So what we wanted to look at is in a second step really at the pairing order, the D-wave superconducting pairing order, where also there's a huge number of papers around it, whether the stripes and the superconductivity are really cooperating or competing, and really to put these two methods together, and this was then published in 2020. Let me get into that a little bit in terms of the methods. I think most of you have seen tensor networks, so let me just briefly remind you that DMRG, or matrix product states, that's of course a one-dimensional method. You do 2 dimensions by mapping the 2D system onto a one-dimensional snake, which has the issue that in order to encode the area law, which you will observe, it's easy if the cut is, say, horizontally, because you cut many of the lines, but vertically, all the entanglement basically has to be put into that bond here. So this becomes exponentially hard for DMRG. So what you can do is you look at stripes. I mean, stripes now geometry, not in terms of the Hubbard model stripes. And because of boundary condition effects, you actually put that on cylinders of a certain circumference. So the results you get are very reliable, but they're extremely limited in size. On the other hand, let's look at this auxiliary field quantum Monte Carlo method. What do they do? The idea is in principle very simple. You evaluate ground state properties by an imaginary time evolution on some initial wave function. What you do is you start initial wave functions basically by superpositions of Slater determinants. The point is, however, if you do that, if you want to stay in a superposition of Slater determinants, which is numerically advantageous, the Hamiltonian has to be quadratic, meaning only contains C dagger C terms or something of that sort, not the n times n, which is a 4-operator term of the Coulomb interaction. So how to get rid of that? What you do there, you do the so-called Hubbard-Stratonovich transformation, which allows you to rewrite the interaction of the electrons in that form, which is now totally linear, meaning it's in the density, meaning it's quadratic in the fermionic operators. The price you pay is you get an additional sum over an auxiliary degree of freedom, which of course, if you do that at every site and in every time step, this is of course exponential in system size, and this is where quantum Monte Carlo comes in. You sample these fields here, or these auxiliary terms, stochastically in order to be able to deal with that. Okay, and what you observe is this is a very small system. This is an old result. If you do that just naively, you get something pretty awful here. Time, meaning in beta is evolving, and the result gets stochastically extremely bad. It's essentially useless. And that's one of the instances of the famous sign problem of Monte Carlo. And so what these people originally came up with, this is now actually also quite old, is that they observed that if you knew the exact ground state and your trial wave function, your time evolving wave function happened to have zero overlap at one moment in time with the exact result, it will continue to do so as time evolves, because you can insert an e to the minus beta h, because it will simply give you a number, because that's the exact ground state. In terms of these auxiliary fields, it means that these paths, which are kind of given by the values of the auxiliary fields, they will split up and cancel exactly. Now this exact cancellation is not captured by stochastic sampling, and that's where the sign problem comes from. So the answer is, well, keep only those paths that do not hit the zero line, and do stochastics with those. The problem is, of course, you don't know the exact wave function. So the problem of the method is you have to come up with some approximate, they call it trial wave function, which you hope is as close as possible to the exact wave function to get the sign problem under control. This is, of course, the big methodological weakness of this method, which we will see where we, with DMRG, can help. So, but anyways, in this simple model, at least, which I showed on the last slide with these huge fluctuations, once you do it with this constraint and compare it to the exact solution, that actually looks very good. So just that you get an idea what is going on. Of course, the way we had to use these methods to get actually something solved needed a lot of algorithmic improvements and checks, and those of you who are interested in these things, you can of course always ask me. For example, for DMRG, beyond using non-abelian symmetries, I would say the one big step was to replace the typical two-side DMRG by a single-side approach, which already gives you a factor of 4 in efficiency. That is on paper extremely easy, but there are severe convergence issues which we managed to overcome some years ago. There's also a big problem in error monitoring, which we also managed to solve a few years ago to make this a really useful method, not just something you can write down mathematically. For the Monte Carlo people, the big progress was actually better ansatz wave function or trial wave functions. And I think the progress which made actually the results in this latter part of the talk, the very recent results possible, is that they have now come up with a way where these trial wave functions adapt themselves self-consistently to the physical problem. This is a very young development, and DMRG then helps to show that what they are now able to do is really incredibly good. I mean, I must say this is then more a kind of an advertising talk for what they are doing with this QMC method. So our strategy is, let's take the quasi-exact DMRG results on cylinders up to width 6 to check AFQMC, and take AFQMC to the thermodynamic limit, because they can do quite large systems. What we measure is, this is the if you also impose the proper sign structure, this is the order parameter which you have for D wave. We trigger it by a pairing field and then extrapolate by taking the pairing field to 0. That's what you would also, for example, do in a magnet. What we also do is we apply this pairing field only on the boundary of the system, trigger the superconducting order, and see how it decays into the bulk. Or what we also do, which is the numerically by far hardest, is that we look at the pair-pair correlations. This is much, much harder, because these objects are already small and hard to get, so this is even way harder. Anyways, to show you what DMRG can achieve and what the amount of work involved is this is a width 6 system at these parameters here. It's 48 times 6 system. So what you see is the bond dimensions that you have to use are pretty crazy, and still you have to extrapolate. In fact, because this was non-abelian, this is in fact a calculation which uses up to a bond dimension of 70,000. Yeah, I mean, those in the audience who have used such methods know what that means, and still you have to extrapolate. But what you see consistently across all the calculations is there's an exponential decay of the pair-pair correlations. It decays also exponentially from the edge pairing field, so it doesn't look like superconductivity. And in fact, let me jump this slide about comparing AFQMC to DMRG. This is in fact what you then get in systematic studies on larger systems. This is where basically you impose this pairing field, take it towards 0, and do it for larger and larger systems. In fact, we have much larger systems nowadays. But just look at these two guys. This is where DMRG is being compared to AFQMC, where these curves sit very nicely on top of each other within the error bars, and then you take this to the larger systems. So what you do is for each field strength, you first extrapolate to the thermodynamic limit, and then you extrapolate in the field. And what you get, this is for some, I should have put the parameter values. Sorry, I didn't do that. But anyways, this is a typical picture where you see how you extrapolate to down here. And the consistent result we found was that there is no pairing order. So the conclusion for the T prime equals 0 summary was that at least for those values which are typical of actual experimental observations for superconductivity, we do not see, we see period 8 stripes, well, as had been observed. We see D-wave pairing, but it does not lead to anything long-ranged. This is not, to be very clear, to say that the Hubbard model does not sustain superconductivity in one way or another. It's known for many years now that for very small coupling in the small U limit, it does. For example, work by Metzen and Hubbard in the late 90s in Munich showed that. So, and actually we also observed in some parameter regimes possibly weak superconductivity, but they had nothing to do with the experimental parameters. Okay, so now because, and this was of course important in the ultra-cold atom context, because for them this T prime, the next nearest neighbor hopping, is a problem, whereas in the solid it's probably present anyways. It has a value of minus 0.2, and the question is what happens to superconductivity now? This is just under review. If you're interested in reading that, that's the archive version of the paper from March. Okay, other people had already looked at this problem with other methods. One of the papers I like very much is the one by Philip Corbeau using IPEPs. IPEPs uses supercells which are replicated into the thermodynamic limit. This is of course a strong methodological bias and a problem which Philip turns into an advantage by using these supercells to stabilize different phases. For example, he can stabilize D-wave, he can stabilize stripes of various wavelengths, and then he simply compares the energies. And when doing that, he says he finds over a wide range of these T primes, in particular also where we should look, a period 4 stripe, and well, he has a slightly different interaction strength, and he finds D-wave pairing in a relatively large dome. Okay, so these were these results, but they, of course, they have this internal problem that he forces this order basically by hand to some extent. There is something which I will jump for reasons of time. Let me just say one thing about that before I get to that. DMRG results on the Hubbard model regarding superconductivity when these are systems of width 4 are incredibly problematic. Most of them are probably wrong. I have no time to go into that now, but this is something to be kept in mind. That's a problem for us because width 6 is what we can just do. We don't have width 8. So in a way, we are really down to one data point. Yeah, that's an issue for us. But anyways, in this combination with AFQMC, we can do better. So that's what we find in our recent work is we also look at the side where systems are electron-doped. This can be achieved very simply by changing the sign of the T prime and still work with holes. This is because of a mapping which is typical for the Hubbard model. And what we find is, well, we find a weak superconducting dome on the electron side. We find a relatively strong superconducting dome on the hole-doped side. This is, in fact, as it should be. And if one looks more closely, we also find that on the electron-doped side, the superconductivity is coexisting with antiferromagnetism. There's no stripes present. The density is kind of almost uniform. If we go on to the whole-doped side, we find for the weaker doping, we find the striped phase. I will come to the wavelengths in a second. There is a very strong density and spin magnetic moment modulation coexisting with the superconductivity. If we increase the doping, there are still stripes around, but interestingly, they are essentially only in the magnetic moment, very good, but not in the electron density. So the method, the approach we use is exactly the same one as we used for the T prime equals 0 paper, but it turns out that the numerics was much, much harder. In fact, with some of these improvements in the methods, this would not have been possible, and comparing the two methods actually led to many of these improvements. Anyways, let me focus on the whole doped side. And what we found, I don't have the time to go into all the details of these pictures. Perhaps you see here is DMRG together with AFQMC. It's interesting to observe, this is about staggered magnetization, interesting to observe the very good agreement in the systems which we can do. But the thing which came as a big surprise to us, in particular to the DMRG people, was when we looked at the stripes. One can define the density of the holes that is present in such a stripe, and then you can work out the number of hole pairs that should be sitting in such a stripe. And what we now observed consistently between AFQMC and DMRG, where we can do both, and then beyond that it's AFQMC, that many of these stripes have a non-integer number of pairs of holes in there. So here's a relatively complicated picture which I cannot explain, but let's say the green points here would be where they would have to, where the results would have to sit if there were integer number of pairs, which you would think would make sense, you know, from these kind of pairs kind of moving together. But most of the results are sitting elsewhere. Yeah, like here, 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 here. The closer you look, the worse it gets. And we interpret that we don't understand that. That had not been observed beforehand, this presence of these non-integer pair stripes. We observe that, we interpret that as a fact that, and this is kind of matches the fact that these stripes are in some sense close in energy, that the stripes, which are strongly present, but the very shape they take and which stripes you get, that is strongly fluctuating, which means that the pairs between the stripes, sort of like, or the holes between the stripes start talking to each other as well, which might have been a mechanism to ultimately establish the long-range pair coherence. But this is hand-waving. Okay. And let me perhaps jump that, say something very briefly. It's an interesting observation that the TT prime J model, sometimes you like the TJ model as a simplification of the Hubbard model, does not produce these features, at the moment at least. That's the current status of the numerics. Perhaps because it takes the large U limit and you need the intermediate U of the true superconductors to actually make this instability happen. So the last slide I really want to show, if you give me this 1 minute, is the one which I found very interesting about the benchmarking. This is a result, again, we cannot go into all the details here. The open and filled symbols are DMRG versus AFQMC. They sit almost on top of each other except here, but it's still the same shape of the curve. What turns out is that the dependence of the results on boundary conditions like a periodic versus antiperiodic is very, very strong. So our numerics ultimately became possible because we averaged over twisted boundary conditions. This strong sensitivity might also explain why numerical results in the past have been so much different. The second thing I would like to show is this self-consistency stuff which the quantum Monte Carlo people do these days. They do not look at the DMRG results, but once the method has converged, they started with a bad value here, and they converge to here, and this is where the DMRG curves sit. So without any fitting within the methods or between the methods, they come to an excellent agreement. Okay, and sorry, I still have to say something about this figure here, which impresses me a lot. First of all, this is kind of DMRG versus QMC for the systems which we can do both. The agreement is very good. The error bar actually is from the averaging over the boundary conditions. But what I like about this picture here is that if you take the small systems, you would say there is no superconductivity. It really takes the big systems actually to get the finite order, which again, sort of like this is a bit an anti-advertisement for the DMRG, but which takes me to the point that we should be really careful about what we say with using these small cylinder systems. Okay, and now I think I have talked enough. I just show you the conclusion, and thank you for your attention.
All right, Oli, thanks a lot. Yeah, time for one or two quick questions.
I see a few.
Very naive, probably question. So you didn't mention anything about tensor network. So
this is a form of tensor network. IPEPS is also a tensor network, which is sort of the one method in 2D which is working, but it has unfortunately this methodological bias. PEPS probably would not have it. Because it doesn't use this unit cell replication thing, but it's far from being useful there at the moment. Yeah. So that's from the point of view of the tensor network community, that's about as good as it gets. What Philippe does and what I've just shown. I think there was over there, and then
yeah,
Fabian.
Thank you for informative talk. My question is, initially the high temperature superconductors were mapped to this Hubbard model, and then you're studying it. But what about the prospect of material discovery of high temperature superconductors coming back once the mechanism is established? So is there any development on that?
This is actually a question which eludes me a little bit. Of course, I mean, the point is once we understand the mechanism, which actually, I mean, I had been very careful to wave with hands because, I mean, we are at the stage that the numeric starts to become reliable. I think that is the honest statement. Numerics as such doesn't tell you the mechanism, yeah? And actually, this is not directly the answer to the question, but I want to say this because this is an important point for Steve White. He has the feeling that maybe if all this stuff depends so strongly on details like the boundary conditions, what are our hopes for an effective model, which would be, I mean, effective model not in terms of the Hubbard model, but in terms of a mechanism. He's becoming skeptical. I, on the other hand, think it's just such a robust and widespread phenomenon. It can't be that there is perhaps not a model, perhaps in other degrees of freedom than what we are talking about here. And then, of course, if we had that model, I don't know. I mean, it might be a good guide for further discovery. But those of you who remember, what is the Matthias rules? Someone here of the older guys? Yeah, there were these rules how to discover new superconductors. I see the older among us know that. These rules, there's I think 4 of them, and the high TC violate each and every one of them. Yeah, so we will have to see.
Thank you.
Hi, Uli.
Hi.
Thanks for this very impressive talk. My question is about the Monte Carlo methods. When they interpolate to large systems, is that problematic or is that straightforward?
No, because sort of like this is the one thing, that's why I didn't talk about it. Or let's put it this, the extrapolations of the D-wave order parameter is no problem. What is a problem, but that's perhaps systematic and physics, that if you ask me, hey, what then in the thermodynamic limit is the stripe and what is the hole density, what is the filling, this continues to fluctuate all the way through the system sizes they have been able to do, but probably our suspicion would be that's not a bug, but that's actually the feature of the system, that the hole pairs fluctuate a lot between the stripes and therefore develop coherence. But the D-wave order parameter as such, I can sleep very, very well with that.
All right. I know there were a few more questions, but we are cutting into the time for the next session. So
I'm still here, so
yes, I suggest you find
Thank
each other
you.
in the coffee break. Okay, let's thank both speakers. I forgot to hand out the marks for both. Please come here.